Good afternoon, everybody. This is Dr. Schulman just reaching out from my office here at SFCC. I came here to get some work done, so I've got a bunch of stuff to grade. Feel free to come. I got tons of space in here. I usually have a bunch of people come meet me, but we're gonna do 4.2, adding and multiplying. I also have the book here, so in case you want to go through stuff, we can go through stuff together. But this is going to be 4.2, adding and multiplying probabilities. So I'm going to share my screen. I did a pretty lengthy overview of probability before. So I think, and where am I? I'm in your notes, intro statistics, 4.2 addition and multiplication. I did a pretty lengthy intro before. I think the only thing we have to remember is that remember for probability, whenever they have you to do adding stuff, it's harder to do. So we're going to be multiplying stuff. If it's for probability questions, it's going to be addition. So wow, my bad. If they use the word and, you need two events. It's something and something else happening. That's multiplying. That's when you know to use the multiply. And if they use the word or, it's always going to be addition. That's how I always remember the difference between these two. Remember probability. I know it's kind of crazy, but it's just what you want over the total. So I'm gonna go look through the book. I'll look at 4.2, see what it has. There's a bunch of problems. I'll do probably half of them or more than half, just to get you going. So how do we get to these book problems? In case you forgot, you go to my SFCC. Oh, I already have it open. I got denied here. Crazy. So we're gonna go to the Zoom. I'm gonna go to my math lab. I'm gonna open the book and we're gonna take it from there. So here we go. Some people didn't get their stuff done. That's a shame. I'm hoping for more people getting their work done. Please, if you need help, let me help you. I've taught this stuff like a billion times, so I'm more than happy to help as much as I can. So how do we get to the book? I'm going to go over here where it says e-text. I'm going to open a book. I'm going to separate this out, put it on the side. I'm going to keep this open and I'm going to go to 4.2 and I'll do my best to explain whatever it is that we have to do. All right, so these were the homework problems from before, I believe. Okay, so here's what we have. Now, just gotta move myself somewhere. And I gotta zoom in on this stuff. No, not search. Gotta zoom. I'm just gonna make it big. And shift plus. I'm just on a different computer, so it's a little bit. Here we go. All right, so as I said, addition is A or B. So A occurs or B occurs, which is easier. So to find A or B, we're going to be adding. That's usually the best way to think about it. And the multiplication is A and B. Nice. Nothing too crazy. So we're talking about compound probability. Now, if you want like more practice with compound probability, I have like tons of worksheets with like marbles and cards and dice and all this stuff. You usually reach in for different marbles. Just know the biggest thing. Okay, this is the biggest thing I don't want to. I'm going to do an example because this will help out a lot. I'm going to make up an example. So let's say, all right, I might as well teach you, do a nice big example first for the differences between these two things. So let's say we have a bag and sorry about my artisticness. I have a bag. In this bag, we have blue, green, and red marbles. So I have 1, 2, 3, 4 blue, or we got circles because they're blue marbles. Let's say we have 3 green. Let's say we have 2 red. Okay. Now the big thing, whenever they give you questions like this, or for cards or for marbles, you just have to know if it says with or without replacement. Now, if it says with replacement, this means the marble goes back in. Sometimes they do it with food. So like obviously if you eat a donut out of a box, you can't replace it. So sometimes you have to like understand what this concept means. But if we're replacing it, this means the marbles are going back. If it's without replacement, guess what? We take the marble we put in our pocket. So let's say we just want blue or a green. All right. This is without replacing. We want a blue one or a green one. It's not like we're doing one and then another. Blue or green. Well, it's always what you want out of the total. That's what probability means. So if I want a blue one, what I want is blue. I got uno, dos, tres, cuatro. 4 out of 1, 2, 3, 4, 5, 6, 7, 8, 9. Did they really do 9? What a weird number. Sorry. And green, we have 1, 2, 3. So that's 3 out of 9. So our final answer for this one is 7 out of 9. And then if we want to change this into a decimal, I can just do 7 divided by 9. We have 0.78 because we got to round up, or 78%. Now let's say we wanted a blue and a green without replacement. Okay, so the blue, it's still 4 out of 9, right? Crazy. The word and, it's harder to do, so I have to multiply it. So I take the blue one out, right? The blue one is now gone. And we're not replacing it, so check it out. So now when I want to pick a green, there's still 3 greens in here, right? There's still 3 greens in my thing, but how many marbles do we have in total? 1, 2, 3, 4, 5, 6, 7, 8. Isn't that wild? Top times top is 12. Bottom times bottom is 9 times 8 is 72. Now, how do we know if 3 goes in? 1 plus 2 is 3. 7 plus 2 is 9. 3 goes into both, so we can divide them both by 3. That's just numeracy. So I know it's 4 over 72 divided by 3. Oops. $24. Oh, we can go again. I guess 12 goes in. Sorry about that. We can divide this by 4, divide this by 4, and we get 1/3, which is 33%, or 0.33. And I just like to double check. Yep. So 72 divided by 12 is, oh, I made a mistake. That's okay. Oh, because it should have been 24 on the bottom. Guess what? Are we human? Do we make mistakes? Yes, we do. We all make mistakes. It just means we're learning. Or for me, remembering. Sorry. So we can divide top and bottom by 12. So it's 1/6, right? And so we just do 1 divided by 6, which is 0.17 or 17%. That 6 is the ugliest 6 I've seen in a while. What should the 6 actually look like? Well, if we talk about Al-Khawazi and actually where these numbers come from, it should look like that. Why? It has 6 angles in it. So this is just a little bit of information, just where these numbers come from. Your 1 should look like this. Why? It has how many angles? 1. There's 1 angle here. A 2 looks like this. How many angles does it have? 2. A 3 looks like this. I'm just drawing it how Al-Khawazi drew it. 3 angles. And how many angles does a zero have? None. So this is the guy. Alquasi came up with the numbers that we use, our base 10 numbers. That's why a 4 should look like that. So it could be like 1, 2, 3, 4. Sorry, I have this little extra piece. But yeah, so all of them look a little bit different. Um, just so you can know what I'm talking about. Let's look at, there he is. I spelled his name wrong. Sorry. Quarizini. Here we go. Here's a nice little picture of that. Way better than mine. There's the 4. 1, 2, 3, 4 angles. There's 5, 6, 7, 8, 9. That's why I always draw a line through my sevens. But that's how they should look. Exciting stuff, right? That's why when I drew that 6 so ugly, I was like, what is that? Okay, let's keep going with the book. Hopefully that was a useful example with versus without replacement using and or. Okay, let's keep it going. So compound event is two or more simple events, or is the addition rule. A single trial A or B occurs. A or B, we can add them, and the outcome is only counted once. It's equal to that sum divided by the total. All right. Now, this is important. A or B, the formal addition rule at the same time as an outcome in the trial procedure. So what does this mean? This is the probability of all A happening, the probability of B happening minus P of A and B. Okay, probably the best way to think about this is a Venn diagram. All right, what do I mean by Venn diagram? Here we go. So here's the Venn diagram. And I'm just gonna pause this video for a second. I'm pretty sure I know how to pause it. All right, so we're back. Sorry for that pause. So I'm gonna keep it going. I said I could show you using Venn diagrams what this really means. All right, so um, let's say this is different types of music people like. Say this is rock music, this is rap music, and this is country. Okay, and let's say we have, I don't know, let's say 20 people like all three. I should use just a color that's not one of these. So here's 20 people like all three. Um, 10 people just like rock and rap that don't like country. 5 people like rock and country, not rap. I don't know. 10 people like this. We'll say 10 people just like rock music. 5 people just like rap music. And what number is that? I guess I should make this 10 so it's clear. And we'll say more people like country. I don't know. I'm not a country fan, but here we go. So how many people are in this, right? How many people are in this group in total? Well, we can add them all up, right? So 10 plus 10 is 20, plus 5 is 25, 30, 50, 60, 80. I got 80 as my total. So 20, 30, 50, 55, 60, 70, 80. So 80 is our total. Now, if they say just rock music, just rock music is like literally this. They don't like anything else. That's 10 people. So how many people just like rock? That's 10 out of 80, which is 1/8. Sorry, that came out so ugly. 10 out of 80, which is 1/8. Okay, nothing crazy about that. What about it they just like it's not they like rock. It's not just rock, they like rock and everything. So we're gonna add the whole thing. So 20, 30, 40, 45 out of 80. We can divide it by 5. That's 9, right? If you don't know 80 divided by 5, just let the calculator be your friend. So it's 9/16. Because that's the whole thing. Now, when they're talking about or, a lot of times, we have to add them, but we can't double count the middle. What do I mean by that? All right. Um, let's say we want to know the probability of somebody liking rock or rap music. So do you see how if it was just rock or rap, right? What if it's probability of somebody liking rock and rap music? Okay, rock and rap music. Well, rock and rap music, you got the 20 people who like all three, right? And 10 people who like rock and rap. So you got to include this one too. So this is 30 out of 80, which is what? 3/8. Is that okay? I hope that's clear. So 30 and rap music. Now, if I count everybody in this circle, right? If I count like literally everybody sorry, will this do what I wanted to do? I sure hope so. Nope. Okay, so if I count everybody in this circle and everybody in the black circle and everybody in the blue circle, right? I'm going to double count the middle. You get what I'm saying? So if I count everybody in this one and everybody in this one, I'm double counting the middle. So that's why it's minus the middle. What do I mean by that? Okay, so we know rock, this is 45, right? I'll put it in black because the black circles this. So the rock is 45 out of 80. We can double count this, right? So 10, 20, 45. Rap is 10, 20, 45. What? It's the same? That's wild. Yeah, because there's 10, 20, 45, 10. The rock is 10, 20, 45, 10, 20. That's the same. So the rock is 45 out of 80. The rap is 45 out of 82. That's the blue circle, sorry. Notice we got 90 out of 80, too much, because we're double counting the middle. So that's why it's A and B minus A and B. So we have to subtract what? This 30 people. So that's why it's the P of A plus the P of B minus the P of A and B. I know, wild. So it's 45 plus 45 minus 30. I would do it another way, but this is how we did it. So what is it? It's 60 out of 80, 6/8, which is really 3/4. So this is 75% of what we have. Now, look what we can take out, right? If I erase this business, right? If I take this out, everything's left. So I can just do 20 minus the total and get what? It's the same thing of saying P of country. And remember, you put a little A here for not, right? Or you can just be like not country if you want. So not country is everything else. So it's just country is 20. The rest is 60 out of 80, which is 3/4 or 75%. All right. So this is what that means. That formula that we're showing, P of A plus P of B minus P of A and B for or, this is what they mean. They mean if I take all of A, right? Is there a shader? Oh, there is a shader. Okay, so if I take all of A, and I take all of B, notice I double counted this middle bit. This middle bit was double counted. That's why we have to subtract it. I hope that was clear. But yeah, let's keep on trucking. Hopefully, making sense for everybody. That's where this formula comes from. All right. Disjoint events and the addition rule. The addition rule is simplified when the events are disjoint. So if A and B don't overlap, they cannot concur at the same time. That's what it means by disjointed. So based on my little picture, right? My weird Venn, this thing is called a Venn diagram. If rock was separate from rap, we wouldn't have to do the subtraction. They'd be disjointed. But Some people like different kinds of music. Mine would have been metal, uh, probably goth and dubstep. I think that's usually what I'm listening to now. But everybody's different. I know I'm old. All right, let's keep it going. Randomly selected a female, randomly selecting a male. That's disjointed, not disjoint. Selecting someone is a statistic course and someone's female. A person can be both. Yes, it is true. Let's see what else we have. So we have complementary events, A or not A. So if we have A or not A equal to 1, that relates to me subtracting like not country to get the 1 from the total. So probability of A plus the probability of not A equals 1. Probability of A equals, so this is just other ways of writing it. So how do we go back to my little example? My little example that wants to disappear for me. Sorry about that. So notice that I said not A. So if I take this, so A happening, so country happening. Oh, that is highlighter. So country happening. We see it's 20. So just country, right? Just country is 20. Somebody liking just country music is 20 out of 80, which we know is 1/4 or 25%. Then somebody not liking country. And if you guys were in a class with me, we would like pick something and we would all like say what we liked. I don't care if it's like movies or TV shows. And that way, and you can see these add up to 1. And that way, if we were to do it this way, you would see the differences. Like we would make up our own numbers and make one of these. And we could make a 4-way Venn diagram. 3 just, I think, makes it look clear. All right, let's go back to the book. Well, this is not the part of the book I want. Let's go back to the book. All right, well, I'm all over the place, so I'm just gonna reopen it. So we're in 4-2, just showing you some rules about probability, teaching you some stuff. I gotta make it smaller. Control Shift minus minus minus. All right, I think I'm good. For some reason it keeps sliding over. Sorry about that. I'm gonna pull it up again. Hopefully I can find the one I was working on. Was it this one? Yes, it was. Okay, cool. Okay, here's the multiplication rule. A is the first, B is the second. Okay. To find the probability A and B occurs in another trial, probability of A and B show the probability of B, found that A already occurs. This is kind of like the with or without. Just make sure this makes sense to you. So what does this little line mean? So P of A and B. So that's probability of A multiplied by the probability of B. And this line means such that, this means such that A already occurs. That's what that means. I guess it's going to get a little tricky for us, but that's okay. This is the difference between independent and dependent. So if I roll a dice and spin a spinner, those two things are independent. If I pull a card from a deck, then pull another card from a deck, that is dependent. We go back to our little picture. Me pulling this out and then pulling it again, it's kind of like the with without replacement. These are dependent results. That's why it changed. That's why this whole thing changed. Okay. Hopefully that's clear for you. All right, let me keep going. Okay. Two of these 50 subjects who used drugs are randomly selected with replacement. Find the probability that the first selected person has a positive result, the second person has a negative result. Repeat part A by assuming that the two subjects are selected without replacement. So without replacement, that means that the total is going to change. With replacement, so the first one here, I'll make this make sense. Sorry. So if we want with replacement, two of the subjects who used drugs are random. Find the probability of the first person had a positive result and the second person had a negative result. Okay, nothing crazy about this. First one's positive, second one's negative. All right, here we go. So this one's without with replacement. Where is it? With replacement. So the first one has a positive result, 45 out of 50. The second one has a negative result, 5 out of 50. You're replacing it. The first, and then if we do it without replacement, it's 45 out of 50. The second one's, sorry, 5 out of 49 because the total drops. That's the difference. You still do top times top, bottom times bottom, top times top, bottom times bottom. But notice that this is from the other group. That's why the 5 didn't drop down, assuming that's what the answers are. Ta-da! Exactly the same. So this is a pretty good example. With replacement, without replacement. When sampling without replacement, sample size no more than 5%, treat them as being independent, even though they're actually dependent. Oof. This is a very tricky point. I'd read this over probably 5 times. So sampling without replacement and the sample size is no more than 5% of the sample size of the population. Treat the selections as being independent. Because we're talking less than 5%, they can claim they're independent. I guess because it's so small. All right, let's see what else we got here. Birthdays. Okay. Now these are just examples. Let's now revisit the chapter problem using XOR 20 babies. All right. There's got to be something new here. So the principle of redundancy is used to increase the reliability of systems. Rise have passive redundancy in the sense that if one of them fails, we'll continue to see. Very often design redundant components so the whole system will not fail at the failure of a single component. I want to understand what this means. The Seagate hard drive model has a failure rate of 2.89% in a year. If your computer has only one Seagate hard drive model, what is the problem that will work for a year? If your computer has two Seagate models or hard drives, it's probably that at least one of them will work for a year. So let's really think about this. So the failure rate is just opposite. So if we're talking it's a 2.8%, 0.029 for failure, then not failing is 97%, right? If we're 2.8, like about 3%, it's going to fail. Not failing's got to be 97. Now, if we have two independent hard drives, right, we actually get to multiply those two together, remember? So they're saying at least one does not fail, right? They're saying at least one does not fail. What does this mean? This means the probability of both failing. Both failing means hard drive one fails. So we need the probability of the first one failing. So we need the hard drive one to fail. We need fail for the first one. If I can spell, that'd be great. Your probability of the first one failing and the second one failing. This is why the probabilities get multiplied. It's one failing and the other one failing. So basically, to get them both failing, what is that? That's going to be 0.0289 times 0.0289. We multiply these two things together, this is both failing. 0.0289 times 0.0289. We get 0.008351. So this is this happening. The probability of this happening is 0.008352. I'm going to show you how I do this problem, not how the book does it. It's 0.08%. All right. Now they're saying we want it not to fail. At least one does not fail, right? At least one does not fail. That means the opposite of both failing. The opposite of both failing. So what is 100 minus 0.08? It's 99.92%. That's what they have, 99.9%. That's how they got at least one does not fail. I don't need the rationale. I feel like I've done enough of these. Oh, they go through all the possible choices. That's fun. This thing is called a tree diagram because these look like little leaves. So this is 2 times 5. So we have 10 of these. Exciting stuff. All right, we get through the problems. I don't want to make this one too long because I never want you to like get too bored. So let's try some. We get 1 through 3, 6, 7, 10. All right, let's start knocking them out. So here's number 1. Notation. When randomly selecting a smartphone, denotes that has a manufacturing defect. Okay. All right, so what is P of D? P of D, that's a defect. Probability of a smartphone defect. And what is P with the line over it? This is not for them. Probability of no defect. Nothing too crazy. All right, let's jump to number 2. When randomly selecting adults, let M denote the event of randomly selecting a male, and B, someone with blue eyes. What do these mean? So P, M, and B, nope. Is it the same as this? No, these are different. So this is the probability of selecting a male given we already have blue eyes. That's what that means. I have to type it. That's getting all fancy. So P, M, they want to italicize. Of course they do. I want to look exactly like theirs. So the second one is such that. So this means the probability of selecting a male given that person has blue eyes. PMB represent, is PMB the same as PMB? They should have had this backwards. So they made a mistake. This should have been B and then M. So this is different from P, B. You know, everybody makes mistakes, even the book. This is what the book was trying to get at. That's going to be they want for answer 2. Everybody makes mistakes, right? Even the book. This is different. So this is the probability of selecting blue eyes given the person is male. I'm pretty sure that's it. You can always go back and check to make sure that that's what it is. Pretty sure the little line after the fact. Line over the top is not. I got that right. The probability of B occurring as occurring A has already occurred. All right, so probability of selecting male given that person has blue eyes, C it already occurred. Uh, the probability of selecting blue eyes given that the person is already male. So yeah, we already have that. That's what that means. All right, I am 2 for 2, even though they mixed up the order for this thing. Let's keep it going. So 1, 2, 1 through 3, 6, and 7. All right, here's number 3. There are 30,488,983 Californians 18 or older. The group selects 10,068 without replacement. There's the big line, without replacement. Are the selections independent or dependent? If the selections are dependent, can they be treated for the purpose of calculations? All right, so if they randomly select this without replacement, it's dependent. So 3 is already dependent because it's changing the group. Now, can they be independent? So this was that part. I was like, you should reread this a few times. There's this percentage. I believe it's 0.05. Yeah, 5%. So as long as we are what? The 5% guideline. As long as this sample size is no more than 5% of our population, we can claim it's independent. So let's find out. We got 5% to deal with. So let's see. Is 1,068 over 30,488,983. Is this, we want to know, is then 0.05. If it is, we can claim it's independent for stats. Let's see. Let's let the calculator be our friend. So you can see the calculator. 1068 divided by 30,488,983. It is to the -5th. It is way less. So what does this mean? This says we have 3.5 times 10 to the -5th. That's what this on the calculator means, which means we take this, we go over once, twice, 3, 4, and the last one's the dot for the 5, 0, 0, 0, 0. This is really 0.00035. That is obviously less than this. So we're going to say it's independent. Dependent for the purposes of calculation. Boom. All right, let's go on to number 6. All right, in exercises 5 through 8, find the complements. So that's the other side. Based on a survey by Consumer Technology Association, smartwatches are used 18% of US households. Has no smartwatch. So if it's 18% is this, what's the opposite of 18%? The complements the other side. 100 minus 18. We make that a 9, we make that a 10. It's going to be how much? 82% don't. Let's try 7, 10, and 15. And I think I'll stop there. 13% know that care instruction symbol on clothing means any bleach can be used. Don't know that? Well, I don't know that. Well, what's 100 minus 13? 87%. Now let's check out 10. Oof. Use the data in the following table, which lists survey results from high school drivers of at least 16 age. All right, assume that subjects are randomly selected. Be careful to read the question correctly. All right, let's see what 10 says. If one of the high school drivers is randomly selected, find the probability of getting one who did not text while driving. So we don't care about the alcohol. We just cared about texted while driving. So first of all, we need the total, right? 731 said yes, 156 said no, 30,054 said no to both of these. And this said no to both. So this is texted yes and no to this. So it's a 2x2 chart, right? To get the 2x2 chart, we can add across and add down and then add your totals. What do I mean by that? Might as well really show you what one of these tables really does. So we got alcohol on top. We got texting over here. Yeah, yes, no. And then I already need more space. I'm going to remake my chart. So we need a yes for alcohol, a no to alcohol. We need a yes to texting, and then no to texting. We have 731 who said what? Yes to both. We have 30,054 who said yes to alcohol, but no, a yes to texting, but no to alcohol. We have 4,564 who said no to both. And we have 156 who answered no to one, yes to the other. So if we want everybody who said yes to alcohol, we add these up. So that's 7, 8, 8. If we want everybody who said no to both, right, that's 8, carry the 1, 6, 7. I'm just putting in the totals. Now, how many people just said yes to texting while driving? That's going to be a 5 and 8, a 7, well, almost a 7. And a 3. And how many people said no to all of them? Well, we've got 0, carry the 1, 12, carry the 1, 11, carry the 1. Wait, sorry, I messed it up. So 10, carry the 1. I'm just gonna add it on the side. I don't want to mess anything up. So 1, 5, 1, 5, 6 plus 4, 5, 6, 4. 4, 7, 20. All right. So if I add this one, right, both totals should be the same. So if I add across or I add down, I should get the exact same number. This is how you can check. So the first total I get was plus 3, 7, 8, 5, 8505. Now if I go the other way, 8, 7 plus 7, 6, 1, 8. 8. Magic, right? This is my totals, this is my grand total. So this allows us, so for any probability, whoa, sorry. So for any probability, we just need the total, right? Because the probability question is just going to be what you want over the total. So for these, all I have is use the 8505 at the bottom for my total for whatever we want. So what do we want to get for 10? If one high school driver is randomly selected, so our total is 8505, find the probability of getting one who did not text while driving. So did not text while driving. So we don't really care about this one. We just want the no texting while driving, which is what? Both of these ones put together. No text while driving and this one. So all I have to do is add these two up. 156 plus 4564, and I'm going to get the answer. So the no text while driving is these two added up. 156 plus 4584 is 4740. Now, this is our answer, but I'm always gonna push you guys because I don't know what it's gonna have in your on your test. So we're always gonna do the simplified fraction, the decimal, and the percentage. So why don't we do the decimal first? And that should this is kind of a trick. So instead of having to divide this by 5 and 10, if I divide this right now to get the decimal, you will see it's 0.55. We're just going to leave it at 0.56. It was even and we could do a trick. So that's 56%. Okay. But this one we will have to break down. So the first thing I'm going to do is I'm going to divide this by 5. 4740 divided by 5. So our top is 948. And our bottom is 1701. Can this be simplified more? 1 plus 1 plus 7 is 9. 9 plus 8. Can we divide them both by 9? Maybe. 189. No, because 9 plus 4 plus 8 doesn't go into 9. I'm pretty sure this is the simplified fraction. This is the decimal, and there's the percentage. All right, let's do one more of these. I did 10, let's do 15. If 2 of the high school drivers are randomly selected from the 887 subjects who drove while drinking, find the probability that neither of them texted while driving. Assume that the selections are made with replacement. Are the events independent? Assume that they're made without replacement. Are the events independent? So if we're making something with replacement, obviously we can state that they can be independent because we're making it without replacement. Let's check out 15 and really see what it's asking us to do. So if 2 of the high school drivers are randomly selected from the 887 who drove while drinking. Oh, so they added these together. That's how they got that 887. Okay. Find the probability that sorry, my email keeps buzzing. Find the probability that neither of them texted while driving. So this is a tough one. We finally hit one that's kind of crazy. But for this, all we have to remember, probability is always going to be what you want out of the total amount. Our total is what? 887, right? And with the first one, we're going to say it's made with replacement. So, ready? 887. And here we go, 887. The total's not going to change. My total does not change because we're saying we're making them with replacement. Now, all we have to do is say that find the probability that neither of them texted while driving. Well, texted while driving. So we have 887 for this one, right? Who drove while drinking, and we want them not to have texted while driving. So drove while drinking is this whole thing, right? And no texting while driving is 156. So what's the probability of not texting while driving? If texting while driving is 731, it's 156. And we replaced it, it's 156. That's the first one. So we just top times top, bottom times bottom. Sorry. $24,336. And the bottom is going to be 887 times 887, which is 786 7, 6, 9. So what is our first one? What is our first example? It's going to be 2, 4, 3, 3, 6 divided by, I'm pretty sure these, I think I can divide them both by 3. Yeah. 8, 1, 1, 2. Right? 7, 8, 6, 7, 6, 9. Oh no, it doesn't work. Okay, so this is our fraction. It happens, right? Sometimes they're big and scary. Let's get the percentage. It is 0.03. 0.03 is less than 0.05, right? So we could say it's independent because it's less than the 0.05 we need. But our value is 0.03. We got 3% for the first one. The second one says we're going to do the same thing, but we're going to say without replacement. So that's the 156 over 887, and we're multiplying this by, we take one out, and our total also drops. $156 times 155. So 24,180. The bottom is 887 times now 886. 785, 882. We can at least divide this by 2 and make it a little bit nicer for the fraction. So let's cut this in half. So the bottom is really 392,941. The top 24180. 24180. 180 divided by 2 is 12. Oh, 90. Now, to see if this is can be divided by 3, 1 plus 2 is 3 plus 9 is 12. 12 goes in. So 3 plus 9 is 12. So this is what I'm doing, just so you can see. 3 plus 9 plus 2 plus 9 plus 4 plus 1 is 28. And what's 2 plus 8 is 30. 3 goes in. That's how I know I can divide both of these by 3. So 12090 divided by 3, 40, 30. And 392,941 divided by 3. What? 392,941. I guess I added them wrong. Is 28. Oh, and 28 is not divisible by 3. So we're fine. So this is it. This is our fraction. Sorry about that. All I have to do is give you the decimal and the percent. These can be tricky, so I wouldn't worry too much about them. I would just really make sure you really read the questions hard. All right, so we have a 0.03%, again, 0.03, 3%, which means we can claim that they're independent events. Ta-da! All right, hopefully, to me, this one is a dependent event because we took it out. We took the one person out. It's without replacement. However, we see it's less than 0.05, so we can claim it's independent through calculations. All right, that was a whole lot. That was a long video. I hope it was useful. Maybe I'll look at 21, make sure it's not too hard for everybody. Use the results from this panel THC test for marijuana use, which is provided by the company drug test. 143 subjects with positive results, 24 false positive, 150 negative, false negative. All right, so all you have to do is make a table. I showed you how to make one here using the numbers. So for this table, when you do it yourself, where's my table? Where's my fun little table? Here it is. Alcohol, texting, yes, no, yes, no. For yours, it's going to be false, positive, positive, negative, false, negative. Nothing too crazy. Just make yourself your own table. Try your best on it. If it gets too hard, guess what? Just let me know. Um, so we got 143 positive, 24 false positive, 157 negative, 3 false negatives. To get them all together, you add them up. So I would just make yourself a table. Try your best with this one. If you really need help, feel free to shoot me an email. That was a lot for probability. They get tough. I promise they get real tough. So really, really try with these. Really try your best. I hope this was helpful, and feel free to email me if you have questions. And guess what? Enjoy your day.